So today I'm going to be talking about sample average approximation with Bendis card for a maximal return. SAA here is sample average approximation. So let's define our problem context first. Suppose we are a Pokemon card collector wanting to collect a specific card for Pikachu, and we want to buy at least 30 of these cards, and we plan to sell them later on in the future. Every day we are given the option to buy the card off eBay, but every day it's going to be a different price. However, we know that we have an alpha level of confidence that the Pikachu card that we're wanting to buy will grow by 10% each year. So the problem is, how should we buy my Pikachu card? Specifically, at what price should I buy them at and at what amount? So there's a few components that we want to consider. We want a way to capture a range of outcomes in the future since we don't actually know what will happen. And how do we know if our solution actually works in reality? Well, the way to do this is we firstly develop a range of samples that we deem as valid. And then from this range of sample, we should ideally be testing our solution and ensuring that a wide percent of them is going to be passing. So the way to do this is to develop a range of sample that we deem as valid. And specifically, we're going to let f be a function that outputs a list of lists. The outer list will contain n number of index, so that means we're going to generate n number of samples. And within the inner list, we will have 52 index. And this just represents 52 weeks. So at each week, we're going to have a different pricing. And so our solution should be able to work on y% of the samples that we have generated here, which in this case is n. And there's a few ways to do this. One way to generate samples is to use Monte Carlo simulation, geometric Brownian motion, or any variations of the GBM technique. I myself have an alpha level. Using the GBM technique, I pull the price closer to the target price. So what that means is, suppose I have an alpha level of confidence at time period t, I'm going to multiply that by the target price, which in this case is going to be 10% of at the end of this year, right? And then we're going to minus it out by the next price. And this next price is going to be what the GBM motion kind of give us. So again, this alpha just represents an alpha level of confidence that the price will move towards our target price, which is 10%. And this is just to kind of show why I want this alpha level, because in this solution, we can kind of see there is no alpha level, and the ending result is roughly normally distributed, which is fine, but I do have an alpha level of confidence that the solution is going to move towards this 10% mark. So yes, great, that's our stochastic part. And so what about the model? What's our Garobi model? Well, we want to maximize our average return across all scenarios, right? And so we're going to need a variable that represents our return on investment. So ROI is going to represent CS for each scenario X. And therefore, our objective will just be to average this. So 1 over the number of samples we have, and sum over the return on interest. And what's our variable? Well, what do we get to decide? We get to decide the amount of stock, A, we want to buy at a price P. And so some constraint that we can come up with immediately is for each each price, we can only have one A value. So therefore BA, PA is going to be set to 1 for each price target. For each price. But then the question becomes, how do I link the BA and Z values? And it's sort of complicated, because there's a few questions that we kind of want to ask ourselves, right? At this period in time, at this week, we want to buy an amount of stock at price P, but how much have we spent so far? I didn't actually know for the simulation. I mean, if I'm spending over the capital by now, I can't be spending any more. I can't be buying any more stocks. And at the end of our 52nd week, which is 1 year, how much income have we generated? Well, we don't exactly know, because we need to know how many stocks we've bought and at what price, aka what's our average price. So this might be doable with basic integer program, but I don't know. I tried it myself and it didn't just seem to work out, so I decided to go with Bendis. And I suppose this is the whole point of this video today. It's an introduction towards Bendis decomposition. More specifically, today I'm going to be mentioning about logical Bendis card, which is separate, well, somewhat different from classical Bendis, where classical is this nice closed form solution, which just always seems to work if you have the right context. And then logical Bendis is just something you need to fiddle around with a bit more. So, how does Bendis work? I kind of think of this as a mother and a child. We're going to have two problems. The first problem is going to be what we call our master problem. And in this case, this is like our child, a daughter, for example, where you have like a 5-year-old who doesn't actually understand the problem that much, and it just does weird stuff and get a solution that may or may not actually work. And then you have the mother here, which is going to be our sub-problem that analyzes this solution and then kind of bring feedback back towards the children. So, for example, we have a kid here, a daughter, that says, I got a solution. And the mother will take that solution and think about it, and she might go do some stuff with the solution. So the solution that the child gave might be a bit complex, or the mother needs to do some complex stuff to understand the child's solution. So we're going to do some stuff, and then it's going to come back, and it's going to tell us two things. The first thing it's going to tell us is, nah, child, this isn't a valid solution. Or the second thing might be, this is a valid solution, but here are some additional information that you might need. And so the child is going to take it, it's going to be sad, and it's going to take these additional things that the mother provides to help the child. So if the child made something that isn't so good, it's not a good solution, it doesn't abide by some of the laws, the mother might teach it, hey, here's a few other laws that you kind of need to learn about in order to build a proper solution. So the child takes that, unfortunately, and needs to go back to do some work before it comes up with a new solution. So from a high level, that is basically how Bender's decomposition works. So let's look at our example a bit more. So in this case, our child, which is going to be the masters, needs to have some constraint and some other variables. To start off, we have the variable asset S, which is the total value of all our Pokemon cards at the end of the year. And the upper bound is this, it will just be the capital, how much money we have, divided by the minimum price that we can buy it at. And we're going to multiply that by the end of the year's price. And that will basically be telling us, this is how much cards we bought multiplied by the price at the end of the year. And that makes sense to just mean that's the total amount of assets we own. So the cost is going to be the direct opposite of that. It's going to be how much we spent in total to buy our cards for each scenario. And the lower bound is going to be the minimum price multiplied by 30. And the reason I have a 30 here is because, remember, we want to make sure we at least buy 30 cards by the end of the year. Right, so then we can generate this initial constraint that we provide to the child saying, hey, our return on investment for the sample S is going to be less than or equal to the maximum asset we can have for sample S minus the minimum cost we can have for sample S. And so we need this because if we don't give this, then the child is probably going to give us some absolute garbage. It might give us like infinity because it's not constrained to not give us infinity. Whereas once we give this to the master problem, it's going to know, hey, I have this maximum limit and I can't actually go to infinity. So there is that initial constraint that we also need to give to the child. And so now we have to look at what about the sub-problem, which in this case is going to be the mum. Well, the mum can do two things. The first thing it can do is it can tell the child, hey, this actually isn't a valid solution. And so if it's not a valid solution, remember the two things that the mum gave to the child in that animation, it's going to one of them give them a feasibility card. And the feasibility card is basically a constraint that removes this solution and, if possible, all the similar solutions that are non-valid. So what does that exactly mean? That kind of means that, if solution A and B are very similar and we know A isn't valid, if we can derive a logical concept that if A isn't valid and B isn't valid, then we're going to generate a card that removes both A and B. But note how I say in brackets, if possible, so this might not always be possible, but it would just be good if you can give it a feasibility card that removes both invalid solution A and B if possible. And if it's not possible, then just remove solution A for now. The second card is going to be called an optimality card. So this is where the child gives us a valid solution, but the value it hands at the solution might be weird. So for example, here is my water bottle, right? And so if I was a child, I might say, hey, this water bottle is worth $10 billion. And this water bottle might be a valid solution. But the price I put on this water bottle is insane, $10 billion, and that's just not correct. So that is what we call an optimality card, where the mother says, this is a valid solution, but you've kind of given it a wrong objective value. And in that case, we would provide a constraint that sets the upper or lower bound, depending on the problem, to the true objective value. So this is all really high level right now, and let's kind of have a look at what actually goes on. So to get started, we're going to assume we have function g, where g takes in two variables, BA. BA is going to be the solution the child gives to us, and we're going to take in price. Price is just going to be a list of 52 index. So it's going to be a single scenario of what could happen to the Pokemon card's price. Right, and so it's going to output something quite complex. This g function is going to basically calculate a dictionary that contains 5 keys. The first key is going to be the cost, and this is basically going to be like, given our solution BA and the price, a list of price, if we follow this solution on this price scenario, this is the true cost that we're going to be generating. And similarly for the stocks, this is going to be how many cards do we actually buy, individual cards do we actually buy, given this is the price list and this is our solution. Finally, we have assets, which is just going to be what is our final value of the bunch of Pokemon cards we have bought. We're going to have this return on investment, so basically this is how much Pokemon card that I have bought, and this is how much these Pokemon cards are worth now. And finally, we have this special thing called invalids, which is going to be a list of all the violations that happen. What does that mean? Well, there's two possible violations that could happen, right? The first violation could be the sense that the solution the child gave to us, along with the actual price scenario, doesn't actually match. So what that means is, you're not going to buy enough stock, for example, for one right now. You're not going to buy 30 cards that you wanted because possibly the price just never met the BA value that the child was expecting. So that's one of the solutions. Sorry, that's one of the possible violations. The second possible violation is going to be if this BA ends up spending too much of the price based on our G function. So when the G function evaluates BA and prices, it might find out, oh, according to this BA, you're actually going to end up spending more than you can actually spend, i.e. the more than the capital that you initially had. So these are the two types of violations that could happen. And so now I'm going to introduce something called the no good card. So this is going to be a feasibility card, whereby the child gave us a solution that is not valid, and we, as a mother, we want to correct the child to saying, here is a correct solution. Here is a new constraint, a new law that you kind of have to abide by in order to generate a proper solution. And so a no good card is basically the card where you remove the current solution. So basically, if a child gave me this eclipse, I'm basically going to say, hey, don't give me this eclipse anymore. It's going to be a wrong solution. And it's going to do nothing else but remove that one singular solution. And this is kind of no good. And the reason for it being no good is because now you're essentially just having the child trial a solution and having the adult telling you, that's not really a good solution. And that just keeps on happening without better cards being applied. So it's going to become a trial and error consistently. So this might take some of you a while to understand, but essentially what's happening is if we have a current, a variable current, which is a list of price to amount from the solution BA, then for all the BA that we have, we're going to sum through them, which is, remember, BA is going to be binary. And suppose that we have 20 pairs of P to A variables, and if BA just so happens to be 20, well then this is no longer allowed because 20 must be less than the length of current, which is going to be 20 as well, minus 1. And so 20 is not less than 19, and so that's invalid. So basically this constraint is going to remove whatever current solution is in BA right now. So what is a better card then? Well, I think it's good to kind of see some examples to have a look. Suppose we have this BA of, hey, if we see a price of 1, we buy 5. If we see a price of 2, we buy 4. If we see a price of 3, we buy 4. If we see a price of 6, we buy 6. If we see a price of 7, we buy 0. Suppose we run our G function and we find out we actually didn't end up buying the 30 cards we wanted to buy. Well then, what else is not a valid solution then? So in this case, I have another BA, which is going to be the exact same as this, except here we have, at the price of 1, we buy 4 cards. Now, if 4 is obviously lower than 5, and if this BA didn't actually buy us enough cards, do you think that this other solution is going to provide us enough cards? Probably not. In fact, definitely not. Here is another example where I turned this 4 back into a 5, but this price of 6 minus 6, I turned that into a price of 6 minus 3. Do you think that that will somehow magically get us to have bought enough cards? Again, probably not, because we're going to be buying less cards. So this also isn't a valid solution, given we know this isn't a valid solution. So the last one is going to be this, whereby here I've changed this at a price of 3 turned into an 8 with a price of 6 turned into a 3. So I've made 2 changes. Do we know if this is a valid solution or not? Well, we don't actually know. It depends on the price scenario, which has a bunch of scenarios out there, and we just don't actually know if this is a valid or invalid solution. We're going to have to run the G function again. So we can't actually say anything about this. We can't cut this off, because when we generate a card, we must make sure we only cut the invalid solutions off. And similarly for spending over the capital amount. Suppose I change this price of 1 to a 7, and now we're having issue with spending over our capital. Do you think this is going to make it any better if we're spending more than what we can spend right now? Probably not, because we're told that this is spending too much, and I'm not going to be getting anywhere by spending even more. And similarly for this one as well, I've changed this 6 into a 10, and it's not actually going to make us spend any more. It's not going to make us spend any less money than we have spent. If anything, it's going to spend us more. So now that we know what are some of the solutions that we can cut off given a solution that is invalid, we can kind of define a better cut now. So in this example, I have for each price amount from our current solution, I'm also going to loop over a dash in A, which is a separate amount in the list of A's. And if if our current amount is less than this separate amount, sorry, this is supposed to be backward, isn't it? Okay, right. Yeah, sorry about the confusion. So if we have a price and amount from our current solution and we're looping over a dash in A as well, if the A dash is less than the value we have stored in our current solution, then we're going to sum that integer up as well and make sure that is less than our current minus 1. And similarly, so for if we spend over the capital, if we have a price and amount from our current solution, and we're also looping over a dash in A, which is the amount in our list of amounts that we are allowed to buy, if this a dash is greater than A, then we also want to add that as part of our solution and make sure that the sum of these integer, which is going to be a list of ones, is less than our current solution minus 1. So finally, we have this last one we want to talk about, which is going to be what is our objective? So again, if the child gave me a water bottle saying this is 10 billion, I would want to teach it saying, well, this is a valid solution, but this is actually only worth $10. And the way to do that is we're going to have to, oh my god, is this another issue? Okay. Okay, here it comes. So, if our objective value is wrong, then what we're going to do is we're going to add an optimality cut. And what does this optimality cut look like? Well, we're saying for this scenario ZS, we're going to make sure our G function is going to generate what our actual spending is for this scenario S. And remember, it's going to return to us a dictionary, and one of the dictionary results is going to contain this ROI. And what this means is we're going to take this true return on investment and we're going to add that to this separate thing. And so what is this separate thing? Well, this separate thing is basically saying, if we sum over PA in our current solution, well then this BA value for PA is all going to be 1, right? And so we're going to keep on adding 1 minus 1, which is going to become 0. And so this entire thing, if we have what we have for the current solution, is going to become 0. And what that means is 50,000, 500k, multiplied by 0 is going to be 0. And we're setting the return on investment for scenario S to be what it actually is, if we have the current solution of BA. So for whatever current solution for BA is, if we get that solution back, we're going to get the true value. However, if the child decides to give us a different solution, so slightly different, then what that means is one of this BA, as we're summing over all the 1 minus BAs, one of this BAs is going to return us a 0. And so 1 minus 0 is going to be 1. And this sum is going to be at least 1 or more, given we don't have this current BA solution anymore, right? And so 500k multiplied by 1 is obviously going to be 500k, and we're going to be adding that into the ROI, which is a pretty insane number. And so what this means is it's not going to affect the return on investment for scenario S if we get a different value, because we're going to get an up or down that is insanely high. 500k for a single investment is obviously a lot. And so, yeah, it's going to give us an insane number. It's going to make the cap really high. And so that's going to be perfectly okay, because if we get a different solution, then we know the cap won't be this, and we're going to rerun our function to actually calculate the ROI. Does that kind of make sense? So by setting it to be so high, you're not restraining the child to say, do not try this different solution that you have. You're kind of more like encouraging it to go, this is a solution that you can still explore. And once you explore it, as a parent, I can take it and actually run this function and say, tell you whether or not it's good, it's bad, here is the true return on investment. Yeah, so by setting the high value, again, you're not discouraging the child to not do it, you're more encouraging the child to say, here is a scenario, a solution you haven't explored, and right now I'm capping that solution to be at this value. It's a solution that you can definitely give it a try. And so with that being over, let's quickly look over my code. So here is the G function that I was talking about. Here is the A, here is price. I'm looping over the price, and I'm just deciding whether or not we're going to be buying that stock based on this price. And then if the number of stock we bought at the end doesn't hit 30, then I'm going to say we need more stock. If our total spending is over our capital, then I'm going to say we're buying too much. And then our dictionary result is going to have the total cost, the total stock we bought, the total asset we have, and then we're going to set invalids to be whatever is inside invalid, which would be need more stock, spend too much, or none of them. And then we also need to set our ROI. And then here is the child, the master problem, which is in this case a child. Again, you can see that I'm capping each amount to be exactly 1 for each price. And I'm setting an initial constraint on how much the value can be, which is the return on interest for scenario X. And then in the callback, this callback is what we call our subproblem. So basically, it's going to be the thing inside the loop where a child gets a solution. Once the child gets a solution, it's going to pass it to our subproblem, which is contained within the callback. And then the callback is going to do its stuff, give it back to the child, the new constraint, and then the child is going to recompute the solution, and it's just going to keep on happening. And so, as you can see in this callback, I'm storing my current solution, and then I'll be running this f function, which in the PowerPoint I call it a g function, and then from there I'm going to check while it is invalid in my g function result. If it is, then clearly there's some sort of invalid stuff happening, and we need to implement a cut. And so if we're spending too much, then I'm going to implement a cut there, and if we're spending too little, then we're going to implement a cut there. And then if there is no invalid result, then what we're going to do is we're just going to do an optimality cut, which is basically saying if you ever get the same solution again, then here is the true return on investment. If you ever give me a different solution, then I'm going to overestimate the true value of your ROI so that the child actually still explores this potential solution. And that basically ends this introductory video on doing a bendis cut with sample average approximation. Yeah, and also just to kind of reiterate, we're looping this through all the scenarios, so it's going to give us the true z value for each scenario, and then in the result, in the objective, we're just going to average this return on investment over all of our scenario. Again, feel free to try a different f function. From what I know, something I would definitely give a try next time is to say, give a y% of stuff to let go. So basically what that means is, right now in the current solution, I'm enforcing all the scenarios to meet the constraint of making sure we bought enough stock and making sure we're not spending too much, right? But that's impractical, especially when you generate more and more scenarios. So the next thing to kind of do is to say, well, let's run this f function over all our scenarios, and then I'm going to give it a 5% level of saying you can only fail 5% of these scenarios, and if you fail more than 5, I'm going to enforce the constraint that I previously already did, which is going to be like these constraint. But if you're failing less than 5%, then I'm just going to let you go and give you the optimality cut and just move on. And that's going to be a lot faster for Garobi to run as well, because Garobi has a high range of, actually I don't really know that, do I? I think Garobi would probably run faster since it would have more space to kind of explore a potential solution and actually arrive at that optimality, instead of running through everything only to find out this problem is actually infeasible, which it turns out for this example I have right now, it is feasible. But again, you never know, because if you're running through all of the scenarios, there is a potential where you're just super unlucky, all the scenarios you generate can't actually match each other with a single BA value. So yeah, hope you guys liked it, and that would be the end of today's video on sample average approximation with logical bendis cut on Pokemon cards. See ya!